Hi, welcome to VSEPR Theory and Molecular Geometry. You have been drawing Lewis structures, which show molecules in a very flat, non-three-dimensional way. However, molecules are not flat. They do have dimension to them. And the reason why is because of the arrangement of the bonded and non-bonded electrons on the center atom. When I mean the center atom, it means which one's in the center. So we have an idea, it's called VSEPR theory, that explains why molecules have certain shapes. And we're going to use our Lewis structures to draw what's called ball and stick models, which are the three-dimensional shapes of the molecules. So you can see in the picture, there are many different shapes for molecules. We're going to focus on a few of them. And it all has to do with what's happening with that center atom. Some center atoms have lone pairs, some do not. Some structures don't even have a center atom. Folks, lone pairs are electrons, bonds are made of electrons. So what happens if you have electrons which are all negative near each other? Like charges repel each other. And because of that, the electrons are going to adjust to be as far apart from the other electrons as possible, which results in the shape of the structure. The theory is called VSEPR theory, or valence shell electron pair repulsion. How do the electrons surrounding that center atom affect the molecular geometry? So we're going to focus on that center atom, and that will help us to determine the shape of the structure. You see bond angle listed here. Don't worry about that right now. You're not going to be tested on bond angles. You'll see them, but you're not tested on them. So the first drawing that we have, there is no center atom. So there's no electrons that can push themselves apart from each other. We just have two atoms bonded. This could be something that's diatomic, like fluorine or bromine. It's just a linear shape, because there is no center atom and there's no lone pairs to worry about. In the next one, we do have a center atom. We do not have lone pairs. In these diagrams, for learning purposes, the lone pairs, if you look at the third diagram, the third picture, you'll see something that looks like a little guitar pick. That is representing lone pairs, non-bonded electrons. So in picture 2, you do not see any lone pairs on that center atom. So the two bonded pairs try to get as far apart from each other as possible, so they move 180 degrees away from each other. This is also called linear. There's two bonded, but there's no lone pairs. In the next one, you do see a lone pair on the center atom. So we have two bonded pairs and one lone pair. Again, those three pairs of electrons want to be as far apart from each other as possible. So the two that are bonded get pushed away from the non-bonded electrons. This is called a bent structure. There's a couple ways you can get a bent structure. There's two attached and one lone pair. In the next one, you have three attached to the center atom. So the three bonded, again, want to be as far apart from each other as possible. Like charges repel each other. So the three bonded push themselves away from each other. This is a flat structure. It's called trigonal planar. There are three attached, but no lone pairs. In the next one, you have four attached to the center atom, and you have no lone pairs. So the four bonded separate themselves, repel each other. This is called tetrahedral. Four attached, no lone pairs. Okay, look back again at bent. In this bent, there's one lone pair. On the next part of your chart, you'll see that we can have bent with two lone pairs as well. The top one, we have three attached, just like we had three attached back here in trigonal planar. The difference between this trigonal planar and this one is this one has lone pairs. This then pushes the three bonded pairs away from the lone pair, the non-bonded pair, and you get something called trigonal pyramidal. It forms a little tripod or pyramid. There's three attached, and then it does have a lone pair. The next one, this would be, water is an example of the next one. It has two lone pairs on the oxygen, and then the 2 hydrogen are attached to the oxygen. So we have 2 attached, 2 lone pairs, also creates a bent structure. The next 2 are those exceptions to the octet rule. This could be phosphorus in the next one, it could be arsenic, it could be anything in that group 15 that acts like phosphorus would in this situation when it's with something highly electronegative, like a halogen. So, you can see that there are 5 bonds on the center atom. It means that each one of phosphorus's electrons, valence electrons, are bonding to produce 10 surrounding the phosphorus. Again, exception to the octet rule. This is called trigonal bipyramidal. It has 5 attached, and that center atom has no lone pairs. The next one's also an exception to the octet rule. It has 6 attached. This could be sulfur. Sulfur's in group 16. It means that all 6 of sulfur's electrons bond for a total of 12. Called octahedral, there are no lone pairs. Now let's apply this. We have a couple example problems. We'll get to in just a moment. We're going to apply by drawing our Lewis structure and then converting that to a ball and stick model. These are some examples of ball and stick models. You're just going to draw simple lines for your bonds, circles for your atoms. What you're not seeing here, though, is the labeling that needs to occur within those structures. So each ball and stick model, for every ball and stick model, you should have a chemical symbol in the circle itself to represent the atom that it is representing. So your first one, here's carbon dioxide. I've already done the Lewis structure for you. Carbon is your center atom. Does carbon have any lone pairs? How many are attached to carbon? There are no lone pairs on the center atom. So the 2 bonded pairs get away from each other as far apart as they can, which creates this linear shape that you're seeing. It has 2 attached. So those 2 bonded pairs try to get away from each other, and it creates what's called a linear shape. To show that in the ball and stick model, you have your carbon in the center and your oxygens on each side. The next one is SF2. What's our center atom? And does our center atom have any lone pairs? Sulfur is the center atom, and yes, it does have 2 lone pairs. So those 2 lone pairs are going to push the fluorines away, the bonded pairs attached to the fluorines. So it has those lone pairs. So these 2 fluorines are going to be pushed away. They're going to be pushed down because of those 2 lone pairs. This is very similar to what water does to create its shape, which is bent. Keep referring back to your chart so that you can understand why the shape is what it is. So this is going to be a bent shape. Sorry, my sulfur is missing a little bit of the circle. So you're going to also label your ball and stick model. Sulfur is in the center, the 2 phosphorus. We do not put any lone pairs on a ball and stick model. Also, when you're drawing yours, you do not have to draw your bonds very thick like that. They can simply be lines attaching the circles between the sulfur and the fluorines. CBr4, this is carbon tetrabromide. Carbon's in the center. We're not focusing on the lone pairs on the bromine. The question is, number 1, we know carbon's in the center, and does carbon have any lone pairs? The answer is no. Carbon does not have any lone pairs. But there are 4 attached, and I apologize in advance, my numbering is a little off. So there are 4 bromines, you can see that obviously. And the shape then, because it is 4 attached with no lone pairs on the carbon, the shape is called tetrahedral. To draw that in a ball and stick model, carbon's in the center. You form a little bit of a pyramid on the bottom with your bromines, and then 1 bromine up top. Notice there are 5 attached to the arsenic. This is one of those exceptions to the octet rule. Arsenic is acting very similar to phosphorus, which makes sense, they're in the same group. Arsenic is your center atom. It does not have any lone pairs. and it has 5 atoms attached. That shape is called trigonal bipyramidal. Arsenic in the center, and the 5 fluorines attached. Again, you can just draw simple lines for your bonds. You don't have to make them thick like these are. BCl3. Bromine is our center atom. It does not have any lone pairs, and it has 3 attached. So this is a very flat structure. The chlorines just separate themselves from each other. They don't form the pyramid because there's no lone pairs on the bromine. So this is called trigonal planar. Your ball and stick model shows bromine in the center and 3 chlorines attached. And the last one is HI. There is no center atom for this one. The only shape that we can have then would be linear. Your ball and stick model, 2 circles with a line attaching them, one labeled H and one labeled I. Again, you don't have to show a thick bond, simple line would be fine. All right, thanks for listening and have a great day.